welcome to our channel. Today we'll be discussing Doppler's effect and electromagnetic spectrum. It's a part of wave. We have discussed 7.1 and 7.2 in the last video, which was all about transverse and longitudinal wave. And today we'll be discussing these two sections, 7.3 and 7.4, from your syllabus outline. Starting off, we'll be going over what Doppler's effect for sound wave is. Now let's suppose we have three conditions. Okay, I'll be giving you three particular conditions, and I'll be looking over what happens in each of those three conditions. So the first condition is when source and observer are both stationary. Okay, so what source and what observer is? Let's suppose I'm standing by the road and a van is coming, or it's basically is on the road obviously, and the van is giving some sort of horn. Okay, so in this case the source would be the object which is giving off noise or which is giving off sound, and the observer would be the one who is actually listening to that sound. So I am the observer because I am standing by the road, and the van which is blasting this horn is the source. So when both of the observer and the source are stationary, in that particular case the frequency of the sound being emitted by the source and the frequency of the sound heard by the observer, they both would be same. Okay, Doppler's effect is basically the change in frequency of sound wave when source is moving towards the observer or when the source is moving away from the observer. In this case, because the source is stationary, therefore the observed frequency, which is denoted by FO, would be the same as the original frequency, which is denoted by a simple F, right? Second case is when the source is moving towards the observer. Now when the source is moving towards the observer, like in my example, when the van is moving towards me, it's coming towards me, then the horn, the sound of the horn being blasted by the van, obviously it has a frequency, right? So that frequency and the frequency which I'm hearing would be different. Now in what ways would be different? The frequency I would be hearing would be more than the actual frequency. So when the source is moving towards the observer, the actual frequency and the observed frequency have a relation of F0 is greater than actual frequency. The observed frequency is greater than actual frequency. And third case is the opposite, when the source is moving away from the observer. In this case, it will be the opposite. F0, the observed frequency, would be way less than the actual frequency, which means the frequency I would be hearing would be lesser than the frequency given off by the horn that is being blasted by the van driver, right? Now we have studied the concept of what Doppler's effect is. Now we'll be looking into the formula and its application. Now the formula is again very simple. Let's suppose we have F0 equals to, okay, this is the formula by the way. Not everything is, I'll be telling you one by one. F0 is the observed frequency. F is the original frequency given off by the source. V is the speed of sound, which in normal cases is 332 meter per second, and Vs is the speed of source by which it is moving towards the observer or away from the observer. Speed of source. Now if in the second case, when the source is moving towards the observer, the formula would be we will have a subtract minus sign in the denominator, and for when the source is moving away from the observer, the formula would be, we have away over here, it would be, we would have plus. Now one way to remember it is that when we basically decrease the value of denominator, the fraction's value increases, and we know that when the source is moving towards the observer, the frequency must be greater than the actual frequency, right? So for that case, we need to increase the value of the fraction. For that, we need to decrease the value of denominator or either increase the value of numerator. Now numerator has a fixed value of 332 in air, right? So the only option left for us is to manipulate the denominator, and in this case, to increase the frequency, we will decrease the denominator by subtracting the speed of sound by the speed of the vehicle or the source. And for when the source is moving away from the observer, the case would be the opposite, because we need to have a greater observed frequency, right? Sorry, a lesser observed frequency, and for that we will increase the value of denominator so that the fraction's value decreases automatically, right? This is the concept of Doppler's effect. Now moving on to EM spectrum. EM spectrum has a number of different types of waves in it. I have a diagram with me. I took it from Google, so I'll be sharing it with you all. It's a very simplified and easy diagram, so you can understand the workings of it. Now radio waves, we have how many? 7 different types of waves: radio, micro, infrared, visible, ultraviolet, UV, which is also called UV, X-rays, and gamma rays. And as we move on from radio to gamma, this way the wavelength decreases, the value of wavelength decreases, and this way, moving from gamma to moving from radio to gamma, frequency increases, which means gamma is the most energetic, the most dangerous one of all the waves present in this particular spectrum, because as we increase the frequency, the energy which is directly proportional to frequency, you learn this eventually as you study probably quantum. So yes, my point being that as you increase the frequency, the energy increases, and as the energy increases, the intensity of that wave to harm you also increases, obviously. Therefore, gamma is the most ionizing radiation among all these. So gamma has a value of 10 power minus 12. Now you need to remember all these values. It can be asked in MCQs normally. They don't ask you in theory section, they'll ask you to fill in the blanks. Like they'll give you a chart like this, and they'll probably erase some of the waves and their wavelengths, and you'll be asked to complete that table. So for that purpose, you need to memorize this chart. So gamma has a value of 10 power minus 12 meter. Minus 10 is for X-rays, minus 8 is for UV, minus 6 for visible, minus 5 for infra, minus 2 for microwave, and the power 3 is for radio wave, the highest wavelength, the longest one actually. Now visible light is again a spectrum of its own. If you open it up, visible light is, now some of you might remember it from WebCure. That's how I remember it, and I've always remembered it like this. It's very easy to remember it like this. WebCure. Now V is for violet, I is for indigo, blue, green, yellow, orange, and finally red. Right? So Vibgyor, moving from violet to red, wavelength increases and frequency decreases. Okay, my writing is horrible. Please excuse that. Violet has the range of wavelength of visible light is from 400 to 700 nanometer. Now you just need to remember this particular value, which is by the way fixed. It's 400 to 700 nanometer. 400 violet starts from 400, then it's like from 400 to 435 or 420 nanometer, something like that. So anyways, violet is 400 and onwards, and red is 700 nanometer. Like it ends at 700 nanometer. Above 700 nanometer you have you have infrared starting, and then below 400 you have UV wavelengths or UV light. Right? So our objectives ask us to state all the EM waves as transverse waves that travel with the same speed of light in the spectrum. All these waves, by the way, now these are transverse waves, right? I mentioned in my last video that examples of transverse waves is are EM waves. Now another differentiating factor between transverse and longitudinal wave, for instance, let's suppose we take EM wave and sound wave. EM is transverse and sound is longitudinal. So one differentiating factor is that EM waves can travel in vacuum as well. Like they can travel in space, because obviously light is coming off from sun, and it's traveling all the way in the space to us in the earth. So it tells us that EM waves can travel in space, and they have a speed of 3 × 10⁸, which is meter per second denoted by C. All these waves, from radio to micro to gamma, all these waves, even the visible ones, all the colors in the visible light spectrum, they travel with a speed of 3 × 10⁸ in vacuum. Okay, and so yes, EM can travel in vacuum, but sound cannot travel in vacuum. Therefore, any explosion, any sort of disruption happening in space, that sound cannot travel to us, because sound cannot travel in vacuum, and space is vacuum, right? Moving on, we have point number 2 says recall the approximate range of wavelengths in phase space. Okay, we have mentioned this diagram over here, but you need to memorize. And third point is recall the wavelength in the range 400 to 700 nanometer in phase space are visible to human eyes. So the only this particular section of the EM spectrum is visible to human eye. We cannot see radio, we cannot see micro, we cannot see infrared, we cannot see ultra, X-rays or gamma. We can only see visible light, therefore hence the name visible, because it's visible to our naked eye, right? And also I forgot to mention one more point in Doppler's effect. Our syllabus is restricted to observer being stationary and source moving. However, we have cases of when observer is also moving towards the source or away from the source. But that's not our concern, because our syllabus doesn't mention the observer moving, as you can see over here. It clearly states that relative to a stationary observer. So you do not need to know what happens when the observer is also moving, because our syllabus only talks about stationary observer. That's all for this 7.3 and 7.4. 7.5 is left, which is polarization. So I'll be making a different video, 10-minute or 5-minute long, on that section, and that will be the end of wave chapter. Thank you for watching. Do let us know in the comment section if you enjoyed the video, or if you have any queries or questions.